Okay, now we're going to kind of extend what we know about first from atoms and then multi-electron atoms to molecules and taking a look at molecular spectra. And actually I'm very familiar with that. I use that quite a bit with my research at NASA, although I'll tell you that up front that I'm a little less strong on some of the chemical bonds that are going on between molecules, as well as the condensed matter aspect. But we'll make it through it. So what we're going to talk about is going to talk about the bonds that hold atoms together, not from a chemistry sense, but more from a kind of a wave function sense. We'll talk about how molecules are different than, say, hydrogen atoms, and at first they could rotate, right? When I have a molecule that might look like this, it can rotate. That's going to affect its energy levels, and that's going to affect its spectra. Or it can vibrate. We kind of treat this guy like a spring and say that these guys are vibrating back and forth, and that will affect its spectra as well. We'll talk about why atoms can form crystalline structures, how there's energy associated with that. We'll talk about semiconductors and how we can have some band gaps for them. And I'll mention superconductivity, but we're not going to do a whole awful lot with that. Kind of some of the questions we'll be answering is why do we care about CO2 when we talk about Earth's temperature? We'll talk about molecules and condensed matter, essentially combining atoms together. And then we'll take a look at semiconductors, which sometimes behave like a conductor and sometimes behave like an insulator. And they're really quite useful for calculators, computers, transistors, anything like that. Now, before we get started, just want to talk a little bit about the types of bonds we're going to talk about in this chapter. We're going to be talking about ionic and covalent bonds, and these guys are going to be relatively strong bonds. And when I mean strong, I'm talking about in the 1 to 5 electron volt range. We're also going to have these weak bonds, which are going to be van der Waals and hydrogen bonding. There are some other types of bonds, and these guys typically tend to be less than 1 electron volt. And I'll talk about these two in the next couple of slides, but what a van der Waals bond is that is going to be the interaction of the electric dipole moments between two atoms, kind of attracting them together. Again, relatively weak. And with hydrogen bonding, we're going to have a proton, essentially a H+ ion, that gets between two atoms, and essentially that's going to polarize it, and that's going to attract them because like charges are going to repel and opposite charges are going to attract. So let's talk really quickly about ionic bonds. We do know that like charges are going to repel and opposite charges are going to attract. And let's take a look at an example, say table salt, NaCl. We know that if they're alone, then we're going to have sodium, which is going to be a positive ion, and chlorine, which is going to be a negative ion. When a bond is formed between the two of these guys right over there, essentially they are going to be sharing an electron, and the sodium atom is going to give up one electron, and it's going to give it to the chlorine atom, and a bond is going to be formed. So oppositely charged ionized atoms are essentially what cause an ionic bond, and this is going to be a relatively strong bond. I kind of like to think of when this chemical bond is set up that these guys are kind of like magnets, where that's a magnet and that's a magnet, and they're oppositely charged, they're going to be attracted, and when they come together they're going to click, and that click is kind of the release of energy. In order to pull these guys apart, then it's going to take some energy from us to be able to do it, so that's going to require energy. Now, this is kind of like falling into a well, and when these guys are attracted to one another, there's going to be some radius with which they're kind of most comfortable with, and that's going to be when they're sharing that electron. If we were to, kind of try to push these guys together, then the system is going to push back. If we were to try to pull these guys apart, then these guys are going to have an attractive force between them. So it's kind of like falling into a well. And inside of this well, there's going to be some most comfortable distance for these guys to be separated by. Now, covalent bonds are a little bit different than ionic bonds. Usually ionic bonds, we're talking about one electron that's being shared. With covalent bonds, we're looking at two electrons, or a pair of electrons that are being shared. And if we were to consider a couple of bonds here, we just consider H2. If we had two separate hydrogen atoms, kind of like that, then we would be able to talk about their wave functions, and that's going to be kind of describing the probability of finding an electron in the lowest energy state. So this one would have one that would look like this, and this one would be identical. And if we were to kind of bring these guys together, then what's going to happen is that the wave functions are going to start to distort, and the pair of electrons could be found anywhere inside of this region. You can kind of see that these guys look a little bit differently. So what they're kind of doing is they're sharing that pair of electrons between the two of them. You can see this distortion of the wave function even more if we were to look at something like methane, which is CH4, and this guy's kind of pictured right down there, and you can kind of see that the wave function, or the probability distribution of this guy, comes kind of egg-shaped, and there's not a whole lot of probability finding it here, 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 and here. So let's take a look at the spectra that we would see that would be emitted or absorbed by a molecule. Keep in mind that emission and absorption are really quite the same, just like it is for a hydrogen atom. And if we had just a regular, ordinary, everyday atom, it might emit a certain frequency, so kind of frequency just like this, and intensity just right there. And it would absorb that frequency as well. That would correspond to some energy levels, and there may be some shifting around due to the Zeeman effect, but let's just kind of ignore that for right now. Now, if you were to take a look at the spectra for molecules, this is going to look a little bit differently. And here's one for HCl that I pulled off of Hyperphysics, and you kind of see that we don't just have one spectral line coming off this guy. Now, it turns out that this guy right here is going to be a molecule, and it's going to have a bond between them. And first of all, this thing can rotate just like that, and there's some energy there. This thing can also, we can treat the chemical bond kind of like a spring, and you can kind of picture these guys going back and forth, back and forth, back and forth. And so we're going to have rotation, and we're also going to have vibration, and there's energy in both of these guys. And so what that's going to do is that's going to shift the energy levels, and we're going to see a spectra coming off of a molecule. It's going to look a lot more like this, where we're looking at some rotational and vibrational energy bands. Also, kind of keep in mind that the real world is a lot more messy. We would have pressure broadening of these bands as well, and we also have different ions, so you can kind of see if we were to look at this little region right over here. Here we're looking at all of these different isotopes of C2, and it has kind of a fingerprint that is associated with it. Now, how much energy are we talking about here? For rotational, we're talking kind of in the 10 to the minus 3 electron volts or less. For vibration, we're talking about, I don't know, about 0.1 electron volts or so. Kind of compare this with the transition between atomic levels, which that would be about an electron volt or so. So we are talking about some energy, and significant energy, but both of these energies as well are far less than what we would expect for atomic transitions going between one shell and another shell. So let's talk a little bit about these rotational energy levels. Something we may remember from a rigid rotator is we would write the energy as 1/2 I omega squared, where this is the rotational mass and that is the angular frequency. And something we also know is we would write the angular momentum as the product of the rotational mass times the angular speed. And so you could kind of convince yourself quite easily that the energy is going to be equal to L squared divided by 2 times the rotational mass. But if we remember that L is going to be related to the quantum number little l, where it was going to be equal to L times L plus 1 multiplied by h bar, then you can convince yourself quite easily that the rotational energy levels are going to be given by this guy right over here, and dictated by the quantum number L, where L is equal to 0, 1, 2, and so on and so forth. Now, when we talk about the rotational mass for a molecule, kind of this is going to be the picture that we're looking at, and it's going to have some center of mass. Maybe mass 1 is more massive than mass 2. This guy's going to be kind of rotating. What we would describe is we kind of describe an average distance between these guys right over there. And we would actually just describe the rotational mass as that average distance multiplied by the reduced mass, where essentially all we're doing is we're reducing the mass of these two guys into one, and that guy's given by this guy right over here. Now it's going to shift the energy levels, and it would maybe have an energy level right here, and this would be L is equal to 0. When L is equal to 1, it's going to shift the energy level up by h bar squared over our rotational mass. and this would be L is equal to 2, L is equal to 3, and L is equal to 4. And that's what's going to give us some of the different frequencies that we were looking at earlier. And again, the energy levels that we're talking about here is we're talking about relatively small. We're talking about 10 to the minus 3 eV. So let's get a little bit of practice by first talking about the rotational spectrum of carbon monoxide, CO. And if we know that the average distance between the two of those, and we'll talk about the two most common isotopes, let's find the three lowest energies and talk about the wavelength of the photon that would cause a transition between the L is equal to 1 to L is equal to 2 level. And first thing we do, just figure out reduced mass, pretty straightforward. And we're going to get this guy right over there and calculate the rotational mass, and yes, it is really small, but we're talking about molecules here. Then we can kind of come up to the equation 42.3 and just kind of plug in for the energy levels, and it's going to be 0.23 milli electron volts multiplied by our L values. And then we'd say, okay, well, L is equal to 0 is going to be E is equal to 0, L is equal to 1 would give us that, and L is equal to 2 is going to give us that. Now, what type of wavelength would give us a 2 to 1 transition? Well, that's just going to be the difference between the two energy levels. And you go ahead and you calculate that guy out, and that's going to be 1.29 millimeters. And I'm actually going to refer to this as long wave radiation. And what I mean by that is that the wavelength is much longer than the wavelength of light, and that's going to be important when we talk about how CO2 can affect climate and stuff like that, as well as CO. So let's take a look at vibrational energy levels, and again, we're talking about 0.1 electron volts or so when we're talking about vibration. And essentially we have these two masses, and they could have been rotating in the previous one, and now we're going to treat these guys like they're connected by a spring, and that's going to be a chemical bond. So picture this guy going back and forth, and this guy going back and forth, and there's energy stored in that spring. Now, how much energy? Well, that's going to be related to kind of the effective spring constant. That's going to be this guy right over there, as well as the mass. And what we can also do is we can also tie this to the quantum number n, and so n is going to be equal to 0, 1, 2, and essentially it's kind of like having some normal modes set up on this guy. One thing to kind of keep in mind is that the difference between the energy levels is just going to be related to that effective spring constant K, as well as that reduced mass. And as we looked for n is equal to 0, then we're actually going to have some energy right there. So we're going to have some energy. It's not going to be 0 like it was for the rotating one. And then n is equal to 1 is going to be right here, 3, and 4. You can kind of see that these guys are nice and evenly spaced, as you would expect from this equation right here. This is slightly different than the rotational energy levels. Now, keep in mind that we can have both rotation and vibration combined, and the result is, well, frankly, a mess. So I'll talk about it briefly, but I'm not going to have you do anything with it. You can kind of see if we have the energy levels n is equal to 2, 1, and 0, and then we have the L is equal to 0, 1, 2, 3, 4, 5 energy levels, we can have all sorts of transitions going on right here. And the result is, if we were to look at the spectra, we're going to see a whole bunch of different frequencies that are associated with all of these different transitions. So now let's take a really quick look at the vibrational spectra for CO2. So we're talking about the same molecule as before, and we're looking at when the vibrational energy changes and the rotational energy is initially 0 and finally 0. And what that kind of tells us is that tells us that delta n is going to be equal to -1. And when the rotational energy is initially 0, what that kind of tells us is that L is initially 0, and then at the end of the day, its final value is going to be 1, and the reverse is true. So the reverse is going to be true for part B. So in case A, energy level is going to increase. In part B, the energy level is going to decrease, although actually the amount is going to be the same because we're talking about plus or minus 1. Now, how much is the energy level going to change by? That's going to be h bar multiplied by omega. It's going to work itself out to be about 1/4 of an electron volt. And then we can say E is equal to hc over lambda. We can always say that and figure out the wavelength. And so here it is right over there. Keep in mind that we're using the value of h in electron volt seconds because we have our energy transition in electron volts, and we can get the wavelength to be 4.6 micrometers or 4.6 microns. And again, this is going to be long wave radiation. Now let's look at some kind of implications of this. Let's take a look at the solar radiation coming into Earth versus the thermal radiation going out. And I've talked about a lot of this when we in the language of emission, but keep in mind that emission and absorption are pretty much the same thing. If a atom emits a wavelength particularly well, then it will absorb that wavelength particularly well. So kind of right over here, on this axis right over here, we have absorption, where we have 100% versus 0%, and we have a wavelength in microns or micrometers. And what we kind of know is we know that the sun is going to have some temperature, and so it's going to peak, have a peak radiation that it is emitting that's going to be essentially a shortwave radiation. It's going to be in the green, 550 nanometers or so. And Earth is much cooler, and so it's going to be emitting thermal radiation going out. This is going to be long wave radiation. It's going to be largely in the infrared portion of the spectrum, so we can't see it. And if we were to look at the absorption spectra for some key greenhouse gases, the most important greenhouse gas is actually going to be water vapor. Most people think it's CO2, but it's not. And water vapor is not going to absorb very much of these wavelengths, so it's not going to absorb in a spectrum that we can see, but then it's going to start to have all these absorption bands going all the way up through this guy right over here. And what that means is a lot of the thermal radiation going out from Earth is going to be absorbed by water vapor. CO2, we talk about that one a lot. Not going to absorb, not going to absorb, not going to absorb. And then it's going to start to have large absorption bands over here, and a really particularly big one right over there, essentially where we peak in our outgoing radiation. And we have oxygen, we have methane, we have all these guys, and we can kind of add all these guys up, and we can say, hey, look, this is the total absorption that we're going to have from all these greenhouse gases, and you can kind of see that we're going to have a lot of absorption out here in this region of the spectrum, which is where we're putting out at. And that's why people are worried about things like greenhouse gases, because that energy is being absorbed by Earth's atmosphere and re-radiating back towards us.